Hello, and welcome to the next session in my webinar series on C++ Standard Template Library by example. Today we're going to wrap up our discussion on function adapters, focusing on various adapters that can be used to encapsulate member functions as well as regular functions. So without any further ado, let's get started. We'll start by taking a look at where you can find the source code, and then we'll move on and discuss the actual examples themselves. So the examples today are in my GitHub repository, of course, in the C++ STL S-09 folder, in the 9.4, 9.5, and 9.6 subfolders. So let's go ahead and take a look at the IDE. So what we're going to do here is talk about something called member function adapters, and they can be used to allow class member functions as arguments to the various C++ predefined algorithms. There are three of these, and the first two have been deprecated in later versions of the C++ standard, but they're still, of course, available. The first example is called Mfun. The second example is called Mfun-ref, and the third example is called memfunction, or FN. I'm going to pronounce it as memfunction, just to be clear. And we're going to focus on all three of those things. And what they're going to do is basically make it possible to take member functions and then use them in the context where you'd normally expect to have functors. So let's take a look at some examples. This is going to illustrate the use of the Mfun-ref and member function adapters. And it's also going to give us a chance to talk about various STL algorithms and some use of C++ lambda functions as well. So first, let's start off by defining the little class, which I call wrapint. It's a little bit like the integer class that's in Java that essentially encapsulates the native int in some kind of a class. In this case, you can see we have a default constructor that just sets the value that's being wrapped to 0. We also have an explicit constructor that takes an int and assigns that value to the data member that's using to store the contents. Take a look down here, you can see the data member is just an int. And then we have a number of different member functions. These are not static member functions, they're just good old C++ member functions. We've got one called showVal, which is a const method that prints out the contents of the underlying value. We have another method called isPrime that does a long-running computation to check to see whether the value is prime or not and returns true or false. And then finally, we have a couple of methods that return whether or not the value is even or odd. And you'll notice that three of these values have been marked with this attribute, no discard. And what that says is you can't use this method without checking its return value, or you'll get a warning, or you'll get some indication that that's improper. And that's, of course, trying to guard against people having method calls in C++ where you ignore the results and go on your merry way. So no discard is an attribute that's added to detect that kind of a misuse. So let's go down here and take a look at the actual program that's going to be the test driver for wrapint. First thing we're going to do is we're going to define ourselves a vector of 10 wrapint objects. So we say avec, give it a value 10, and it's going to be wrapping wrapint. It's going to be encapsulating it. And then we go ahead and define ourselves a wrapint, just a single instance, and we're going to give it the value of 10. And then just for kicks, I call isEven without using the value in any way. And you can see here that I get a little warning from the compiler saying value of function declared with no discard attribute is ignored. So that's obviously an indication that that's not the right thing to do. We'll ignore that other stuff for now. We'll ignore the no discard ignoring result. So once we've done this, we're going to go through the range 0 to less than 10, so 0 through 9, and we're going to go ahead and create a wrapint for every one of these objects and store it into the corresponding subscript location in avec. So avec sub 0 will be wrapint 1, avec sub 2 will be wrapint, or avec sub 1 will be wrapint with a value of 2, and so on and so forth. And then what we do is we go ahead and we use the ForEach algorithm to print the contents of our vector. And you can see we're doing this by using the Mfun-ref adapter to encapsulate the showVal pointer to member function and then be able to treat that as though it was a regular good old functor. So we'll take a look at Mfun-ref in a second, but first let's go take a look at ForEach. ForEach is a very simple algorithm that, as you can see here, goes through a range from beginning to end. And for every step along the way, it calls the function that's passed in as the third parameter. So you can see it's parameterized by input iterator and function. And of course, the function's a functor, but it could be a function. Also, you can also pass a pointer to a function to the ForEach algorithm as well. And down here, you can see we just go through the range, and every step along the way, we call the function on the next element in the range, and then we increment the count, or we increment that element by 1 here. And you'll also see that when you're done, it returns the contents of the function, which can be used to pass values back to the caller if there's some internal state being used in that function that's being collected. And we'll take a look at some of that stuff later as well. Okay, so what we're doing here primarily is just using this to call the show val for every element here. And you can see that this is what memfunref does. It basically goes ahead and encapsulates the member function in such a way where you can have it called. And if you go here and follow this a little bit, you'll see that we have operator function call defined here, and it goes ahead and invokes that operation using the pointer to member function syntax. Okay, so that's how that's going to work. Down here, we're going to do another kind of operation like this where we're going to use the RemoveIf method. And what we're going to do here is we're going to go through the vector from beginning to end, and we're going to go ahead and encapsulate the isPrime member function. And so as you can see, what that'll do is it'll go through that range, and for every element in the range that's prime, we're going to remove it from this particular sequence. And what you get back here, of course, will be a pointer, an end pointer, and an iterator to the new end of the region, the new end of that sequence, with all the prime numbers removed. And I think you can imagine what RemoveIf does. RemoveIf does some stuff, but basically it's going to go through and copy over the elements, copy them down. Let's see if I can get lucky and find the actual implementation of RemoveIf if it's not lurking in some strange location. So you can see here what RemoveIf does is it goes ahead and first sees if the item's even there in the first place at all using the findIf method, which we've talked about before. And then what it does is it goes through the resulting range if it found it, and then it goes through and basically sees if the predicate matches. And if the predicate matches, it's ignored. If the predicate doesn't match, then we go ahead and copy the contents down. And so what that does basically is it only copies the things that were not the predicate. So that's why we're removing if it matches. So we're going to remove the prime numbers. Then we're going to go ahead and print the contents after we've removed the primes. So everything I've shown you so far is still using the memfunref function adapter. Now what we're going to do is we're going to switch gears and we're going to use the memfunction or memfn adapter. And this is really just the newer way of doing it using the newer versions of C++ features. Let's go take a look at Mfun. You can see that Mfun is annotated with things like no except, and it's going to make an instance of this memfun object or memfunction object, which will then do more or less the same thing that memfunref did, but this allows us to use newer features in C++ and templates to make this work. So this time we're going to go through and remove everything that's even using memfunction, and then we go ahead and show the results using memfunction. So just demonstrating the kind of newer way of doing the same kind of thing. And then the final example here is going ahead and using the C++ lambda syntax, lambda function syntax. So what we're going to do here is we're going to go ahead and remove everything that's odd, and we're going to do it by using a lambda function. So you can see we go from the beginning of the vector to the end of the vector, and every step along the way we write ourselves a little lambda function, which serves as the predicate, and it's going to take a reference to a wrapint, which of course is what's in the range that is being iterated over via RemoveIf, and we just plop the code right in there, and you can see that if it is if it's odd, if wi is odd, then we're going to go ahead and remove it. And then the last thing we're going to do here is to show how you can write the code using lambda function syntax for going through and printing the contents that are no longer going to be odd. They're only going to be even. And down here you can see we just pass in wrapint ref and then say wi for wrapint.showVal. So let's run this code and see what it does. Oh, you can see it was complaining about the fact it was complaining about the fact that we didn't check the return value, which is good. And then down here you can see that we had an original sequence that was the values 1 through 10. We removed all the primes using the Mfun ref adapter. Then we removed the even values using the mem function or memfn adapter. And then the final thing we did is we removed the odd values using a C++ lambda function. So this is just demonstrating some other interesting examples of how to apply these various function adapters that work on member functions. Okay, so that's the first thing I wanted to cover today. Now let's go ahead and move on and talk about some variants of this approach. And we're going to focus on something called the pointer function adapter. Now this is an interesting adapter that has also been deprecated in later versions of C++, although I'm going to show you how it works, and then I'm going to show you a couple different variants to use newer features in order to make this work, such as binders or lambda functions. The intent of the pointer function adapter was to make it possible to take C-style pointers to functions and allow them to work in the context of the various functors you would pass into standard algorithms. So just to refresh your memory, because we've covered this a few days ago, this is just a very simple example of a C-style pointer to function. So we have a function called myFunction, pretty boring. It takes an int I and it returns Boolean whether or not the value passed to it is greater than 10. And down here we define ourselves a pointer to function that takes an int and returns a Boolean. We pass in myFunction to it. We could have said address of myFunction behaves the same way. And then down here we can go ahead and call this as if it was a function call, but in fact it's a pointer to function call. And I can either use this function call syntax, or I can also use this type of syntax as well. So I can call it this way, which makes it a little bit more obvious that it's a pointer to a function, or I can call it like this and make it look like a function. Either way, it works just fine. Let's go ahead and call it, and we get the result back, which in this case says that the value 11 is greater than 10, which is something we probably already knew. All right, let's now go ahead and take a look at another example in this family of examples. This example does kind of the same thing we just looked at, except now it's going to apply this same syntax on member functions as opposed to regular good old C-style functions. So we have a class called example class, which is going to have a explicit constructor that takes an int and stashes it away in a private data member. And then we have a func here called first func, which is a member function that just checks to see whether the value I is greater than X. So this is much like what we looked at before, except now we're doing it in the context of a class and a pointer to member function, as opposed to just a good old pointer to function, which is what we just looked at. So down here you can see how we define this pointer to pointer func, and I probably should be a little bit better about naming this. Let's call it pointer mem func, so for member function. And let's go ahead and rename everything. And then we're going to assign that pointer to member function to the address of example class : first func. So that's obviously going to be a member function, and we're taking the address of that and storing it in our pointer to member function. We then define ourselves an instance of example class, giving it a value of 10. And then we go ahead and use the syntax here to show how to make the call. We say array, because that's the name of the object, dot star, that's pointer to member function syntax, pointer mem func, and that will then go ahead and call first func. So let's go ahead and see what happens when we run this. And it should come back and say that this is in fact true. So it's true because in this case is true because 11 is greater than 10. So that's why it's returning true. Okay, so that's the example. I just wanted to show you these concepts before we look at the pointer fun adapter. So keep that in the back of your mind as we take a look at the next example that we're looking at. So now we're going to go ahead and look at pointer fun, which is defined here. And this is a really fun example. I've always enjoyed showing this example because it really demonstrates the power of C++ STL and its zero overhead abstraction mechanisms that give you all this cool type safety and all this cool adaptation and code synthesis and so on without you having to do very much work and without little or no overhead, without having any overhead at all at runtime. So this particular example is going to demonstrate the use of various function adapters we've talked about so far, including not one and bind second, not function and bind, as well as the C++ generic lambda functions and decal type. And I should also say, it'll also show, naturally it's going to show pointer fun as well. Okay, so let's go ahead and take a look at this example. And this is, like I said, this is a really fun one. So we're going to come in here and we're going to define ourselves a vector of const char stars. So this is demonstrating that you can use STL containers for more things than just int or employee record or double or other kinds of objects that have pass by value semantics. Here we're going to actually store pointers to character literals. And the pointers to character literals will be the strings, the character literal strings 1, 2, 3, 4, 5. So that's what's being stored in AVEC. And then we go ahead and we print out the contents of AVEC with a little prefix saying the sequence contains 1, 2, 3, 4, 5. Now what we're going to do is we're going to demonstrate various ways of being able to search for elements for strings in that vector. So let's start off first by taking a look at pointer fun. That's the main focus here. So what you can see we're doing here is we're looking through the vector from beginning to end, and we're going to go ahead and use pointer fun to encapsulate strcomp. So here's pointer fun. As you can see, pointer fun is an adapter function that's going to create a pointer to binary function, passing in the various parameters. And pointer to binary function is basically going to encapsulate these kinds of things so that we stash away the function we pass in, which in this case, of course, is going to be the strcomp method. It gets stashed away here inside of this particular object and for this functor adapter that we're using. So that's what we do. We're going to create a functor that encapsulates the strcomp C string comparison function. And then we're going to turn around and we're going to use bind second to bind it to the value 3, to the string literal 3. So we're binding strcomp and its second parameter to the value 3, the string 3. And then, of course, because of the interesting semantics of strcomp, we're going to use the not one negator adapter, and we're going to take the results of this strcomp, and we're going to say if it comes back with a 0, that means true. If it comes back with non-zero, that means false. And of course, the reason we have to do that, as you probably know if you've worked with C for a while, is that strcomp returns 0 if two strings match. It returns less than 0 if the first string is lexically less than the second, and it returns greater than 0 if the second string returns is greater than the first string. So therefore, it matches if it returns 0, so we have to negate that in order for findIf to come back and determine we found an actual match. So I think that's pretty cool. And just look at the little string of chained adapters here. So we're converting the strcomp string into a functor using pointer fun. We then use bind second to make that into a bound functor that's bound to the character string 3, and then we use the negator to take the result of that and negate the expression. And all of that's being passed as the third parameter for findIf. And then we should find the results, of course, and then we print out the results from that point onwards using the iterator that came back up to the end of the vector. The next example we're going to look at is going to replace the use of not one and bind second and pointer fun, for that matter, with modern C++ means to do the same sorts of thing. So in this case, we're going to apply the bind method, which is this modern, more modern way of doing things with C++. And we're going to say, I want you to bind strcomp, which no longer has to be treated specially. You no longer have to use pointer fun with it, with the bind method. And then we say, make the first argument the placeholder, because that's what's going to be passed the value for every element in the range from beginning of the vector to the end of the vector. And then we're going to go ahead and bind that to the string 2. And then we're going to take that bound comparison functor, and then we're going to use not function or not fn in order to negate it. For the same reason we did before, because strcomp returns 0 when strings match. But find if expects those values to be true if there's a match. So that's what we do there. We go ahead and use that. And then the third approach we're going to show here is going to be using a generic C++ lambda function. So here, rather than having to use binders and negators and so on, we just say, the heck with it. Let's just go ahead and use a lambda function that's going to be passed an auto s, which in this case, of course, will be a const char star, because that's what's being stored in AVEC. And the implementation here does a strcomp comparing s with the string literal 1. And if it matches, of course, it'll return 0. So we use the bang operator, the exclamation point operator, to negate that result, to give true if the strings compare equal. And then once again, we go ahead and print the results. Let's go ahead and run this code just to see what it does. And I think, as you can see here, what it does is it first prints out the sequence we're going to be searching, 1, 2, 3, 4, 5. And then it goes and looks for 3, and it finds 3, and it gets an iterator back to 3, as you can see here. And then it goes ahead and prints from that iterator onwards. Then it goes and looks up the string literal 2, finds that, gets an iterator back, prints that to the end. And then the final thing we do is we look for string 1, which of course it'll also find at the beginning, and then we print the results. Speaking of printing results, let's go see what we use here as our print operation. We looked at this the other day. This is a clever approach that takes an iterator range, a pair of input iterators, as you can see here, first to last. And it also takes a string, and if first doesn't equal last, we go ahead and print out the string as a const. It's a const string ref. And then we do copy from the first iterator up to but not including the last one, and we're going to print the results to the standard output with a space between them. So that's how we get the results here. And as I showed you the other day, we use the very clever decal type mechanism to automatically create the type that we want to be passed to OStream iterator. So it expects a type like int, or in this case, const char star. And so the decal type is how we convert star first, which of course in this case is going to be const char star, into the actual type that's acceptable to be used in the OStream iterator template for its constructor here. That's a lot of cool stuff. I really like this example because it shows that you don't have to use C++ containers only for types with value semantics. We're also, in this case, passing pointers around, and that's perfectly legitimate. And this is a particularly good example of how all those pieces can fit together in a very, very flexible way, showing once again how cool STL is by not really differentiating between built-in types like const char star or int pointer, and then user-defined types or types that come out of the STL library itself. Okay, we have one more thing to talk about today, and then we'll be done with function adapters. So what I want to do to kind of wrap up is just give you some tips on how to write effective functors. We've seen a lot of different types of functors here. We've seen that there's some functors that take state, some functors that don't store state, some functors that are going to be parameterized, some that are not. You know, there's lots of different variants of types of functors. Some take 2 parameters, some take 1 parameter, some take no parameters, and so on and so forth. So here are a few things to keep in mind when you work with functors. First of all, a functor needs to have the operator function call method. If it didn't have that, it wouldn't really be a functor, would it? And that allows them to look like they're functions, even though they're actually objects that can store state. Make sure when you work with functors that you think about the copy semantics. In particular, if you're going to allow copying of one functor to another, and oftentimes you need to be able to do this because many of the STL algorithms expect to have value semantics for their functor parameters, make sure that you do the appropriate deep copy if you have any state in the functor whatsoever. In particular, be very careful not to allow shallow copies where you'll end up with aliasing that'll get you into trouble if you end up double deleting pointers that weren't properly copied. It's usually a good idea to either make your functors stateless altogether or have a relatively small amount of state in the functor. If you start defining functors with giant arrays or other data types in them, you're going to get a lot of overhead when you copy these things when you do pass by value semantics in the various STL algorithms. So not a good idea at all. The other thing to remember is, as a general rule, to be violated if you know what you're doing, make sure that your functors don't have virtual methods. Many functors just have a single method that's the operator function call method. But even for the ones that have other methods, it's generally a good idea to make sure they're not virtual methods. And that's because you'll get into trouble if you start copying around objects with virtual methods. Now, there are ways to get around this if you really know what you're doing. And the way to do it is to use the gang of four bridge pattern. So in that particular case, what you would do is you would define an abstraction object that would have a pointer to the parts that have virtual methods in them. And then all the methods that are non-virtual in the interface of the functor would simply forward to the corresponding method that's in the implementation portion. That's a pretty unusual thing to have to do, but it's possible. So be aware if you ever find yourself tempted to make functors that are going to need to do something complicated with shared state or with virtual functions, that you apply the bridge pattern to solve that. So here's just a very simple example just to kind of wrap things up. This is a very simple stateless custom functor that returns true if its parameter is greater than 2. Again, I'll show you how to do this, but you normally wouldn't write this kind of code, and I'll show you why in a second. So here's how to use this functor. Let's say we have a vector with a bunch of values in it. So we can go ahead and count the number of values that are greater than 2 by using our custom functor. We can also use a predefined functor like greater together with bind second. That's another way to do this. That's kind of the C++ in the 2000s timeframe way of doing things. The more, quote, modern way of doing things is to use the bind method, where you could say, I want to bind the greater functor to 2 with a placeholder in the first location. That's a more modern way, but that, like I said, that's kind of fallen into a bit of ill repute for various reasons. So here's maybe another way to do things, which is just to go ahead and be very concrete and get rid of functors altogether and use generic lambda expressions. And I guess in this case, if I'm really trying to be generic, I should say auto, not int, and let the compiler deduce the actual type that's being manipulated in that range. So these are all the different ways that you can work with functors. I hope you've enjoyed our discussion of functors. That kind of rounds out the discussion of the various adapters that we have in C++ STL. So if you think about it, what have we covered? We covered STL functions and templates first, the parameterized types. We then talked about sequential containers. We then talked about all the different types of iterators, such as input, output, forward, random access, and bidirectional iterators. Then we talked about the associative containers, both ordered and unordered. And then for the last number of sessions, we've been really focusing largely on adapters. We talked about things like container adapters, such as stack, queue, and priority queue. We talked about various iterator adapters like OStream iterator and iStream iterator and all the variants of that. And then we've been focusing since that point on the various function adapters, such as negators and binders and pointer fun and all that good stuff. So where we're headed next is we're finally ready to cover the final major category of C++ STL capabilities. And that, of course, is algorithms. So what we're going to do in our next session is we're going to start talking about algorithms in STL. And we're going to begin with our focus on the different types of algorithms. There's mutating algorithms, there's non-mutating algorithms, there's algorithms for sorting and searching and sets and so on. And so we're going to go through each of those different types of algorithms and take a look at lots and lots of examples. Now, the good news is you've already seen a lot of this code before. We've already looked at a lot of algorithms. We've talked about things like transform and findIf and countif and so on and so forth. So some of this is going to be kind of recap, and it'll just give you a chance to put it all together and see the comprehensive nature of the various categories of algorithms in C++ standard template library. So if you've enjoyed this content, please go ahead and like and subscribe, and also don't be shy and feel free to go ahead and follow me on Twitter, because I keep people notified with new videos when they come out there. So again, thank you very much, and I will look forward to seeing you again soon.